Hey folks, this week Rob joins me and we talk with Tom Herbert about XDP2. It's a framework and a compiler for making networking really, really fast. You don't want to miss it. So stay tuned. This is FLOSS Weekly, episode 847, recorded Tuesday, September the 16th. This is networking. It's time for FLOSS Weekly. That's the show about free, libre, and open source software. I'm your host, Jonathan Bennett, and today we're going to talk networking and data, fast data, probably some artificial intelligence because we can't have a show without talking about AI and LLMs. We've got as Randall used to always say, a wonderful and talented co-host. We've got Rob Campbell, Robert P. Campbell, the man, the myth, the legend. Welcome, sir.
Hello, good to be here.
Yeah, it's good to have you back again on the show. One of my ULS companions. Get into all kinds of trouble together over there. Today, we're getting into trouble with XDP2 and Tom Herbert. Rob, what do you know about XDP2?
Little to nothing. I have not really done my homework, so once I learn more what it is, I'm sure I'm going to have a lot of questions.
Rob is going to handle the audience proxy part of the show today, and I'm going to fake my way through being the more expert interviewer. But neither of us know a whole lot about it. But that's all right because we have the real expert, the guy that actually knows what he's talking about. This is Tom Herbert. Welcome, sir, to the show.
Hey, thank you. Thanks for having me.
It's good to have you back. Not your first time on FLOSS Weekly.
That's true. I was here in May.
Yes. So
I did promise that we would have some follow-up, so you can consider today to be the follow-up.
Today is the follow-up. So remind us, what did we talk about in May? I think it was some similar things. And then what's new?
It was all the precursor work, the needs for programmability in the data path, where AI machine learning workloads are taking us. But it was kind of a setup for XDP2. And by the way, the fact that you don't know a lot about XDP2, I would point out we're actually 8 days into it since we actually announced it on the world. So I don't expect everyone to be immediate experts on it. That comes in time. We do have a plan on that.
Good.
Yeah. So what is XDP2 and what's the problem that it's trying to solve? Obviously, we've got a problem of some sort for you guys to have written this new thing, but what is that problem?
So let me preface that by a little bit of history, if you don't mind.
Sure.
So obviously, when we started networking back in the early 90s, Linux, everything was kind of done in the kernel. Mm-hmm. And we developed host stacks. So there were FreeBSD, the BSD, Solaris. I was actually at Sun working on it at the time. And there was Linux. And before the Great Fork, pretty much all networking was done initially kind of on Sun's workstation.
Wait. What is the Great Fork? This is the first time I've heard that term.
So this goes back to... Imagine early 90s. The internet is just starting.
Right.
And a question comes up, what do you do for routers and routing? Mm-hmm. So this little startup called Cisco came along and said, we need to build dedicated devices for routing. We think there's going to be a big market. And of course, the vendors at the time, and I think there was a quote from one of the Sun execs who said basically, no, you don't need specialized hardware to do networking, even routing, just use a workstation. That might have been Andy Bechtolsheim, although I've never actually found it on the internet, but somebody made that quote.
Right.
And whoever it is, they kind of obviously ate their words, but that's kind of typical in this industry. So I consider the Great Fork as the first time we went from a single model, how everybody's doing it. We forked, and after we forked, then we started having very specialized hardware. And that specialized hardware actually went on its own tangent. We probably talked about the problems that created over time and how we're trying to unify that now. But the great fork was the routing world and the host world had that fork. So the host world, which I've been more involved in, that proceeded very well. So for me, I started all this back at Sun, like I said, went through a series of startups. And what we found was for a long, long time, the internet and all the network communications could easily be built based on Linux or Windows, but all the networking stacks. And what I found was when performance started to be important, around 2005 or 2006, somewhere around there, we started caring about real networking performance. This is about the time that Google was coming up. So they were looking at low latency, high throughput. We were starting to push video to the internet. The first instantiation of that, we were fine with just basic computers, CPUs, running the OS, and we didn't need anything special. There was a lot of features and developments we made, and I would say from about 2005 to 2020, I call it the golden age of networking software. We were making leaps and bounds, performance improvements just by better code, by revamping congestion control, parallelism. We introduced things like RPS and RSS. So we made a whole bunch of fixes, I would say, to network software stacks, kind of like the canonical networking software stack running in the kernel. TCP predominantly, obviously, and even then it was still IPv4. So we were happy. I remember when I was at Google, we'd have vendors come in, they'd try to sell us the latest and greatest hardware with all these advancements. And most of the time, we really didn't need them. And even if we needed them, the problem that we hit with a lot of vendors was they really didn't have a way to program it. And that was kind of fundamental. We did want things to be programmable. And as long as we were able to use the hardware of the time, we were to meet the requirements, nobody was complaining. So it was working really well. But the problems started around 2020 when AI and machine learning started to come into the picture. And the problem is these workloads have really, really high requirements. They're so high that we can't achieve the crowd performance levels just by being in software and a CPU. So we actually need to start using hardware accelerations, hardware offloads. We need to get the performance going. Now, that was when the problem became evident. But I would say about 10 years ago, we really started to see the problem on the horizon started to appear. And there's three technologies that are pretty much the same age. So one of those was DPDK. DPDK, about 2015, I think it was invented by Intel. Their idea was the kernel is too slow. We need to bypass it. We need to bring networking completely into user space to get more performance because we think performance is going to be a key driver. And DPDK came along. The idea was expose hardware queues to user space, have a library, and we can do networking really fast, but it completely bypasses the kernel, which we've been relying on for the previous 20 years. So that started, and they're doing pretty well. They got a fair amount of traction. About that same time, I'd say 2014, 2013, eBPF came along. That's probably pretty well known, especially in the Linux circles. So eBPF, the idea is we can reprogram the Linux kernel on the fly, even from users. It's safe to do. And now if you look today, eBPF has a huge following, super critical to common networking, in fact, or common kernels. In fact, somebody mentioned the other day that they believe that kernels have not had any great advancements in the past 20 years. I had to point out eBPF. It's revolutionized the kernels, and in fact, I believe it's going to fulfill its destiny as the way microkernels should have been done. It's microkernels done right when we take eBPF to its fullest extent. So that's a little bit separate. I do have what I call my 5 predictions about where eBPF's going. But let's stick with networking for today. So almost 10 years ago to the day, February 11th, 2016, this thing called Express Data Path, or XDP, was born. And the reason I remember that date is because we were actually at a networking conference, all of the Linux networking nerds, and we were discussing the latest and greatest patches and what have you. And on February 11th, Linux Foundation announced that FDIO was joining the foundation. And FDIO was kind of like a precursor to DPDK. They eventually adopted it. But the idea was, let's develop a library to bypass the kernel because the kernel is too slow. But the real kicker of that announcement was they said the FDIO would be 100 times faster than going through the kernel. And like I said, we were at a networking conference and we saw that and we just kind of looked at each other because it made no sense. It's software running in the CPU and user space versus software running in the CPU and the kernel. There's no difference. The only reason the new thing would be faster was because it bypassed all of the layers of the kernel. But frankly, 100 times was ridiculous, maybe 10 times. But anyway, the good news about that is it inspired us to create XDP. And actually on the bus ride to the social event, we hatched out the basics of XDP. It was real time. Alexei Starvatov and I, we came up with XDP. It's pretty simple. Just have a hook deep inside the receive path in the driver. And when a packet's received, call that hook. We process the packet directly instead of going through 20 layers of kernel infrastructure. It's really fast. It's about as fast as DPDK, but it's still part of the kernel. And frankly, it's a little bit easier to use in the sense that you don't need special hardware. So XDP and eBPF, they've taken on a life of their own, quite successful. The third contender that I need to mention is something called P4. That's also another one of these 10-year-old technologies. This was invented by Nick McKeon and his team at Barefoot. And what P4 is, it's a programmable protocol processing. Let me get this right. Programmable packet protocol processing. So 4P, so it became P4. And the idea was they were going to build hardware, programmable hardware, for the high performance data path. And their initial target was switches and routers. So they were kind of on that side of the fork that I mentioned. And their idea was, well, routers and switches, they need programmability. If you're building a firewall, you want to have control over which packets are dropped and the mechanisms and the processes. And for routing, they need that too. So they founded the company. It's eventually acquired by Intel. And today they have a good following. There's quite a bit of P4 hardware out there. But the thing about P4, as opposed to DPDK and eBPF, it's very, very specialized. And in fact, they invented a language for it called P4, which is domain-specific language. And the idea was, if you want to program this hardware, then you need to use this domain-specific language. So P4 also, a little more recently, they realized that there is a market in the host side, the other side of the great split. So they are now trying to get into the IPU market, infrastructure processing units, and the DPUs, trying to be the programmable hardware on the host side. And DPUs are kind of an up-and-coming thing over the past 5 years when we started to realize that host networking stacks running in the kernel or even user space aren't going to be fast enough to meet the AI machine learning requirements. So fast forward to today. Like I said, we can no longer meet the requirements. And I would say there's 2 categories. One is the AI machine learning that I presented. So we're developing new protocols, new techniques for AI machine learning. There's scale up, scale out networking, the throughput expectations, the latency, low latency expectations, the low variance expectations, they're really through the roof. Such to the extent that it's basically impossible not to have some sort of hardware assist for these protocols. On the other side, there's another use case we're finding. Imagine that you've been developing one of these three technologies for the past 10 years. Say you've invested a whole bunch of time and effort in eBPF. Now the problem a lot of people are facing is, what if they need to do something else? What if they find that eBPF isn't sufficient? They need to go to DPDK because they can get better hardware accelerations, or they need to go to P4 because they need the performance. So what the conundrum that people are facing is, I have a mountain of code that I wrote for one platform. I don't want to have to rewrite 100,000 lines of code just to run on a different platform. That basically does the same thing. It just does it on a different platform, and hopefully they get better performance or better functionality. But fundamentally, they're trying to take the same code and port it. Mm-hmm. And that is unpleasant. One of the companies we're working with, they've cited this as, if we can solve this problem with XDP, then it's a win. If we can unify all these models such that the developer only has to write their code once and it runs across all these different platforms, that's a good thing. So it's really those two things. It's AI, machine learning, driving the requirements to move closer and closer to hardware, which means a higher performance. And it's also the need to have kind of multiple targets and give the companies and the sites deploying technology, give them the options, I would say, to deploy different targets, leverage different use cases, and not be bound to one particular technology indefinitely. Yeah. So you can say we're kind of trying to, in a sense, democratize networking, and we're actually trying to do it on both sides of the equation. So that's the history. Now let me give a little bit about XDP2. Mm-hmm. So I call XDP2 programming for the high performance data path in software and hardware. What that means is it is considering programmability. It's not necessarily CPU. We also consider programmable hardware. But we want to target this to the highest performance data path. So we're going straight to the heart of it. It's not an exception path. It's not the slow path. We want to be in the fast path. We want to allow users, developers, to write a program that can run in their fast path with the maximum performance allowed by their hardware. We want but we want it to be easy and portable to give them the greatest freedom. So we can divide the problem up into two sides. One is the developer writes their program. And the other one is they compile that program and eventually it gets into bits executable that's loaded into hardware. So on the front end, we're really adamant it has to be as easy to use as possible. We want the user we want it to be a joyful experience to write this sort of code. If they're writing a firewall or a NAT device or a load balancer or a new protocol for machine learning, we want it to be super simple for them, intuitive. What we don't want is for them to have to worry about all the nuances of the hardware or have to deal with whatever variances there are. We also don't want to force a specific language on them. This is what I think was one of the things that held P4 back, and even to an extent kind of eBPF, because it's kind of bound to C. In the XDP2 model, we want to let the user decide what language they want to use, and XDP2 is not a programming language, but it is a programming model, and as long as we can create an API within a language that supports that model, then we're good to go. We can support Rust, C, P4, Go, even a lot of it could just be a simple GUI interface. So on the front end, let's give the user the freedom to decide how to program their data path and make it easy for them. On the back end, we want to build their code, which was intuitive for them to write. We want to build their code into optimized target code. And that has to be considered, we need to consider that on a per target basis. So we have a concept of backend compilers that can take the output from the front end compiler, which is like an intermediate representation, and then we're going to compile that into different targets. And for each target, we're going to be aware of the capabilities of the target, the features, what hardware it has, what it can do, and we're going to produce optimized binary for each target. So if somebody's writing their code for say, a load balancer, they might do it in C or Rust. We compile that into an intermediate representation, and maybe they have two targets. Maybe they want to run that at eBPF on some machines or DPDK. Maybe they want to run in P4 or an FPGA on some other machines. But our goal is to take that same code that we started with and be able to compile it to all those different targets. And in each target, they get the maximum performance possible. So that, in a nutshell, is what we're trying to do. Obviously, it's a little bit of a challenge. And people, there's an obvious skepticism. It's been tried before. You can't hide the hardware from the user. Yeah, I get it. But you know what the thing is, we've been doing this a long time, and technology has advanced. Even over the past 2 years, the things that we can do today that we couldn't 2 years ago, it's mind-blowing how quickly we're moving. And if you throw in the fact that AI might be able to do some of this, I think it's feasible. And I think it is a challenge. If it wasn't a challenge, I'm not sure we'd have a reason to be attempting this. But most of all, I think it has to be done. We're at a point where networking is the bottleneck in a lot of things. It does not get the performance that we need. And we know we cannot put all this stuff in fixed function hardware. That doesn't work. We need flexibility. We need performance. Now is the time. It's 2025. I think we need to take a shot. So that is all about XDP2. We are trying to provide that. We're basically trying to unify all of these disparate technologies, and individually they're great. P4, DPDK, XDP, individually they're great. But none of them solve the fundamental problem from the user's perspective. They don't want to have to deal with all of those. They don't want to have to deal with having to make fundamental choices that could be disaster in terms of cost. So it really is something that's needed. It's challenging, but that's why we're here, and that's why we're having this discussion. So that brings us to today, and 8 days ago we did announce XDP2 at a SIGCOMM eBPF workshop. It went well. And simultaneously on the day, we did release code to GitHub. So it is open source. There's quite a bit of code. I would point out that it is a new project. Like pretty much any other open source project, it's going to start in slow start. It takes a while to get traction, but we need to start somewhere, and we need to get on the path. We will pull in applications. We will have an application kind of marketplace. I think that's needed. It's reason it's XDP2, by the way, is it does kind of follow in the footsteps of XDP, in the sense that XDP was the express data path. Frankly, it was always my intent that XDP was not just eBPF. It was express data path. It didn't quite turn out that way, but I don't mind, because it did become quite popular with just eBPF. So XDP2, it's not really eBPF. It's trying to go beyond that. It's not the kernel. Like I said, it's not hardware. It's really trying to be a unifying layer to leverage all of the goodness that we've had, solve some fundamental problems, particularly in offloads. And hopefully, I think if we do it right, it becomes it becomes a major innovation and probably potentially disruptive, at least in the data center.
Yeah. So I want to dive back into the history just a little bit because I'm sort of connected with a little bit of this. I play on the periphery of a lot of these things. So in October of 2015, 10 years ago, I was at the first OpenWRT convention, which was side by side with the Linux Embedded Europe, the Linux Embedded Europe convention. They're in Dublin, 2015. And one of the things that the OpenWRT guys was facing was, so obviously OpenWRT is a Linux-based router on very, very lightweight hardware, like MIPS hardware. And some of these hardware vendors, they would have network accelerators, NAT accelerators, basically, to be able to push more bits through this very lightweight hardware. And one of the problems with OpenWRT was it had no support for programming those accelerators. And so at this, we said, why, we asked the core devs, like, why don't we have any drivers for this? Like, what's the problem here? What's the holdup? And their response was, the Linux kernel doesn't even have a framework yet to be able to program these things. And I thought about that when you were telling the story, and I think these three solutions that you told us about, they're sort of all out of that need for some sort of framework to be able to program, to interact with these this hardware-based acceleration stuff. I was sort of kind of, like I said, just on the periphery, but I was sort of kind of there at the beginning of all this, I think.
Well, so what you said is fundamental. And that's funny because that was, 4 months before XDP came into being. But unfortunately, the problem that you're referring to, we haven't actually solved. Over the past 10 years, if you look at kernel offloads in Linux, they have not been a wild success. We have a few offloads from the stack, checksum offload, obviously, TSO worked, RSS. But anytime we've tried to go to something more advanced, even TC Flower, kernel offloads have failed. And the reason isn't because we don't have the hardware or we don't have the motivation to do it. The reason is because it's a mismatch between what the kernel is trying to do and what hardware is trying to do. From the kernel's perspective, I have a piece of hardware, and that piece of hardware says it does XYZ, some sort of complex XYZ function. Let's say it's doing LRO, large receive offload. Wouldn't it be great if the hardware could do LRO, coalesce TCP packets into large chunks, and give them to the kernel so the kernel only has to process one TCP packet instead of a bunch? We've had this idea for probably 15, 20 years, and there have been LRO implementations, but it's not widely deployed or widely used by Linux. And the reason isn't because the hardware doesn't exist or it's not doable. The reason is because the kernel can't trust that the hardware does it right. And I call this the fundamental theorem of offloads. The kernel, like Linux, can only offload its work if it knows that the device is going to do it exactly the same way. The functionality has to match perfectly. If there's any deviation in the slightest, what we found is you can, in tests, the stuff will work great. But once you take it into production, little deviations from what the kernel expects can be disaster and cause wild variations. And this isn't just a theory. I saw this at Google. One time we had a device vendor that was trying to do pacing, TCP pacing on output. And they came to us and said, hey, we have this TCP pacing, pace packets at microsecond intervals so you get a nice smooth transmission on a connection. That's great. So we put it into deployment, and every so often we would hit a packet that was delayed for like 10 milliseconds instead of 1 microsecond. So we went back to the vendor and we said, what's up with this? we're hitting this problem. And the vendor said, yeah, we knew about that, but it's like a 1 in a million occurrence. So we didn't think it would bother you.
This is Google. We transmit billions of packets.
A 1 in a million occurrence in a hyperscaler is a common occurrence. It doesn't work. But the point is, it's that mismatch between the hardware developers and the host side of software. And we've never resolved that mismatch. I think XDP2 will. In fact, I'm planning on doing another presentation just on fixing Linux offloads via XDP2. I think it's doable. But the more critical part here is, and again, this goes back to my statement that we have to start integrating hardware more and more into the critical path. In order to do that, it's only going to work if we have hardware-software co-design. We have to have the hardware vendors, the software guys, they have to start working in tandem really closely. And if you really want to get to the end goal, which in my vision is a world where we just completely blur the lines between the software stack, like Linux, and the hardware, it just becomes one continuous spectrum data path. Its purpose is just to provide users functionality and make things go as fast as possible. To get to that goal, we have to get these guys talking. And I think there's a lot of good direction here. But what that does mean is, more and more when we talk about open source, we should be pulling hardware into the conversation. So it can't just be an open source piece of software running in isolation and not caring about what's below it. Especially if you're talking data path, we need to get more and more involvement and come up with a unified model, not a unified implementation. And that's a big difference because we still want to let solution providers innovate. But can we at least have them do that in a way where we can have uniformity and so the programmer doesn't have to get vendor lock-in or things like that. So 2015 is interesting because, like I said, that seems to be a turning point where a lot of these problems started to bubble up. And today, I think we're finally able to realize the right way to solve these problems. So it took 10 years.
Yeah. Boy, there's a bunch of different directions I want to go. One of the other things I have a little bit of background is for a while I was experimenting with using something like Suricata, which is an intrusion detection system. But one of the things that it would do is you could put it on a network connection and it would just use a CPU and sift through all of those packets. You could use it it was almost like a deep packet inspection sort of tool. And there was work being done on how do you scale this up? How do you use one machine to do deep packet inspection on a 10 gigabit pipe? Back then that was a lot. Nowadays we would be asking, how do you do it on 40 gigabit? How do you do it on 100 gigabit? I don't know. There's probably a 400 gigabit spec by now. I've not looked recently. And
800 gig.
800 is what they're up to.
800 terabit. Yeah, it's coming.
Okay. And so the question was how do you scale up a Linux CPU to be able to handle all of that? And the answer was always, you have to use one of these frameworks, one of these things that lets you do zero copy, right? That was the big thing. Don't copy memory. Have the NIC dump into memory, and the kernel just passes that pointer over to user space. User space works on it without having to copy it, and then it just flips right back. And you could push, the idea was you can push as much data as you want to that way. Is that still sort of the golden solution here? Is that one of the things that XDP2 is trying to allow people to do?
Well, that's definitely part of it, but I would say zero copy is understood technology at this point, and that has been one of the big advancements over the past 15 years. It's a lot easier to do on transmit than receive, but we do have even socket extensions to do zero copy. So eliminating data copy is kind of baseline. But XDP2, even if you eliminate that data copy, you still have to do the processing. And something like intrusion detection, that could get into some really in-depth computational processing. We may need to do regexes, a lot of database lookups. So the back-end processing, so once we get the zero copy, once we do good packet steering, once we eliminate a lot of the cache misses from load balancing. The problem moves to the actual processing of the data. And you can compare this to the whole world of GPUs, right? So GPUs also in this time period that we're talking, they came along, and the reason they're successful is, again, because how they process the data. And the nature of the data in GPUs, high volume, multidimensional data, that really works well with having a bunch of little parallel processing engines that can do matrix multiplication. And it's a data problem first to get the data to them, but then it's a processing problem to process all of these things in parallel and then do some collective operations to collect them. So GPUs are in a sense the poster child of where we want to go with networking the data path. The reason, by the way, we can't really use GPUs in the data path is because it's fundamentally a different problem they're trying to solve. So if you look at the intrusion detection, what it actually is it's looking at packets, usually packet headers, HTTP headers. Sometimes we're looking for strings, but it's looking for things and little bits of data often, like URLs or ports or things like that. So the problem we have in the data path isn't processing large amounts of data in parallel. It's actually processing really tiny amounts of data, like even down to single bytes and bits. Now, like I said, in the golden age, it wasn't a problem because CPUs could easily handle the load. But when you start talking about trying to get upwards of 1 billion packets per second through these things, millions and millions of operations per second, having the data placed and getting zero cache misses, it's just a baseline functionality at this point, in a sense. The real functionality is moving to how do we accelerate the operations? How do you accelerate a regex expression to get the really high performance? How do you accelerate lookups? How do you accelerate compression, encryption? And not only how you do that, how do you put this into a program so the user can write their program, use those sort of functionalities that are probably going to be implemented in hardware? How can they do that without having to know about the hardware or write their program in a non-generic way? So that's the real challenge. So XTP2 itself, by the way, it enables and facilitates performance like in hardware, but itself, it's not the thing that's doing that. It's providing the framework and the model to enable those things. So it's not defining the accelerator, it's defining how you would program to invoke the accelerator. So it's a subtle distinction, but I think it's important because, again, we kind of need to separate out the user's intent, what they want to do, from the implementation. And the implementation, in the end of the day, really has to be targeted, especially in the high requirement space, really has to be targeted to that particular domain. So if I was doing intrusion detection, like Suricata does, I would definitely want an accelerator that does a fast ternary lookup, fast LPM lookup, definitely something that can do regexes. It's a little bit different than what we'd see in a simple load balancer or AI machine learning protocols. But at the end of the day, it all has kind of that same look and feel. How do we process data in motion, the data path, which includes networking? How do we process data in motion in the easiest and fastest way possible? And if we do that, then yeah, the applicability space includes things like the intrusion detection, load balancers, new protocols, firewalls, and all of that. So really trying to solve a fundamental problem in domain-specific architecture where the domain is kind of that network and data path.
So this is a new project only announced 8 days ago, I think you said. It's not even, the code's not even alpha stage, right? We're just mostly planning.
I don't know what's alpha stage.
I don't know. I mean, can it do anything yet?
Yeah. It can do a lot.
It can. Okay.
Yeah, take a look at it. We had to start at some point, and then the starting point was parsing. It's one of my favorite topics. The reason it's important is every packet has to be parsed. So every packet that's received, we have to crack it open. We have to look at the headers. We have to decide what to do with it. And this kind of goes back to my lament, one of my laments about the Great Split back in the 90s. When we had that split and hardware started to become dedicated and specialized for routing, they realized they have to take a lot of shortcuts. So especially in parsing, they decided that we can't actually have programmable parsers. So the number of protocols that these early routers could process were extremely limited. They would allow IP and TCP, no IP options. Eventually, IPv6 came along, and we had to twist their arm to get them to support IPv6. Eventually, QUIC came along. Google had to twist their arm to support QUIC. But the problem wasn't that the protocols were ill-defined. The problem was, in order to make sufficiently fast hardware, especially when you're switching packets, you have to get that in hardware, and you had to make shortcuts in order to make it feasible. So again, that kind of built out the internet. So I'm not going to complain too much. But today, we're kind of stuck. And there's this thing called ossification of the internet because of this tendency to bake things into hardware, not allow programmability. Because of that, in a sense, we cannot evolve the internet in certain regards without a major fix. And the pushback is, well, a lot of these things are hard. Type length values, TLVs, any hardware vendor will tell you they are terrified of having to process those. They're serialized processing, variable length headers. They have all the attributes that hardware doesn't like. And what that means is, we're not going to support that. Now, again, they were saying this 10 years ago in 2015. They're still saying this today. Eventually, you have to think some of these problems need to be solved. So that's one of the things that I'm hoping we can resolve is how do we get beyond this fixed, ossified internet? How can we extend it? And I think a lot of that has to do with how do we enable programmability? How do we enable flexibility? So it's a story that's been ongoing. I think XTP2 is a turning point, hopefully, in that story. And we need to grow it. But going back to parsing, yeah, it was kind of the first thing that we addressed. I think it's actually the right way to do it. If you look at the last blog I wrote, if you're going to program a parser, it's the right way. In time, we also have some technology that shows how to do this in hardware that we'll talk about. But from my point of view, if we're going to solve any problem first, hopefully we can solve the parsing problem and never look back. We can make it go as fast as possible and be easily programmable. Once you go beyond parsing, there's also the what I call the 5 pillars of XTP2. So one of them is the parsing. One of the others is table lookups. So another common action in the data path, we have to do table lookups, meaning we have to do the longest prefix match table lookup if we're doing routing. We have to do a ternary table lookup if we're doing some sort of filtering. Exact match is quite common. So there's all these table lookups. It's a very expensive operation. It's ripe for hardware acceleration, which in the XTP2 model means two things. One is we want the programmer to be able to define their table in an agnostic way, separate from the implementation. So they just say, I have a longest prefix match table. I'm going to be routing based on it. Here's the key length. Here's the expected number of entries. Here's the expected number of turnover rates. That's my program. Hardware figure out, or backend figure out the best way to implement this to give me maximum performance, because this is important to me. So we already have the implementation, the front-end implementation of the tables. In time, vendors or will add back-end implementation to show how tables can be implemented. The third pillar is called accelerations. We kind of already touched on those, but we need to do ancillary processing. We need to do compression, encryption, erasure coding, a whole bunch of accelerators like that. These exist, and like I said, offloads have tried to use this, but they really haven't worked. And in the XGP2 model, what we really want is the user to say, I want to encrypt this block of data, starting from this memory location for this length, encrypt it, and tell me when you're done. That's all the user wants. Why not let them say that? Why not just let them have make it look like a function call, they do it, and then again, when we get to the compilation process, we'll figure out what's the best way to instantiate this in the hardware to get the maximum performance all around. So it becomes a problem of mapping the user's intent into the various hardware accelerators.
Go
ahead.
Sorry. Go. I guess you still had a few more pillars.
I got two more pillars, but okay. Go ahead if you have a question on that.
No, go ahead.
The next pillar is flow logic. This kind of goes back to some of Jonathan's points. So how do we optimize that processing required basically for decision making? And the way I look at a modern networking stack, it's comprised of kind of things we would accelerate in hardware, like the parser and accelerators. But there's also kind of some open-ended logic, how to do things. So when we do intrusion detection, if we hit a match on a regex, somebody has to decide, what do you do? Do you return an error? Do you take some other action? So there's a certain amount of logic. Sometimes in P4 parlance, this is called match action, where the match is a table lookup or a sequence of table lookups, and then actions are kind of, what do you do? And the problem that P4 hit was, or the conundrum was, match is actually something that's fairly easily describable and compartmentalizable. I can describe a match as a table lookup. Actions, though, are tricky because they're all over the board. We have a myriad of different types of actions we could take. Sometimes we forward a packet, sometimes we modify it, sometimes we drop it, sometimes we log it. There's no algorithm that describes how to do an action. So it really has to be kind of almost like a free-form instruction. So I call this the flow logic. And it seems like something that you have to put into some sort of processor. But it also seems like something that, given the very domain-specific nature, you can still optimize and have like optimized instructions to even speed that part up. So it still is kind of like it has to be software in a sense, but we want to still accelerate it with some kind of micro hardware accelerations. And the last one kind of goes along those same lines. One of my other favorite topics, and I'm sure, Rob, you'll appreciate this one for your high performance background. Parallelism is so key in the modern world. It's one of the pillars of computing in general to get performance. So we have to parallelize as much as possible to get performance. And this is a fun problem because the thing we're trying to parallelize, say network processing, data path processing, those are inherently serialized processing. So if you think of network processing, technically we have to process one packet, then the next packet, and the next packet, and the next packet. We have to process packets in order. But even more than that, when we crack open a packet and we have all these headers, we have to process the headers in order. That means we have to process the Ethernet, followed by IP, followed by UDP, followed by an embedded GRE, followed by another IPv6 header. So we have to process them in order. There's no obvious skip ahead. So getting parallelism out of this system is a really super tricky problem. This one goes a little bit beyond what we can do in things like DPDK and eBPF, because we're talking really fine-grained levels of parallelism. But when we get into the high-performance AI machine learning workloads, where we're going to have a lot of hardware acceleration, probably not be supporting this with a commodity OS or even a commodity CPU. If we're running something in bare metal, then we're going to have a lot of opportunities to introduce new models of parallelism. Some of it will be very fine grained, and that'll get the performance up, particularly per packet processing latency. We can really drive that very low. So if you put all this together, this is what I call the 5 pillars of XDP2. They are on a foundation of software, hardware, co-design. That's the foundation for this. And then what they're supporting is that model of new protocols, high flexibility with high performance. So that is kind of like the abstract architecture of what XDP2 is trying to do.
So XDP2 is open source, and so I assume others can get involved if so inclined. Is this written in C or what's?
So I will mention it is in GitHub. It's primarily C. We do plan P4 extensions to it. The GitHub is xdp2-dev/xdp2. That's in the blog also. There is an email list, xdp2@list.linux.dev. Like I said, it's a newbie. It's a new open source project. We do plan on getting others involved. Governance as an open source project will work out in time, and how to make contributions. Right now, it's mostly about evangelism, getting the basics. There is quite a bit of stuff in it. It's not just those marquee ticket items of the pillars. There's quite a bit of utilities. Some of them I mentioned in my articles. Some of them are really pedantic, but when you're programming at this level, they're actually quite useful. I'm planning on next week's article will be on something called parameterized macros, really low-level stuff. But if you're a long-time kernel networking programmer, I think you'll appreciate these sort of things. So there's a lot of goodies, what I call goodies in it. There's also a lot of fundamental models. And frankly, there's a lot of work to do on both sides. So on the front-end side and the back-end side. It's a work in progress, and there's no silver bullet to solving this problem. Obviously, we haven't made much progress in the past 10 years in some regard. So I'm hoping that 10 years from now, when we have the next FLOSS discussion, we'll be saying, I don't know how this is going to work with quantum computing or something.
That's a whole different.
I'm assuming we'll have solved the vibe AI programming by then. So probably on quantum computing and XDP2.
Yeah. Okay. So we talked at high level. I actually want to get down into not the weeds, but like where the rubber meets the road a little bit. And what does it look like to actually use XDP2? So is it essentially an API that sits on top of C code? Is there an XDP2 compiler that I run? How does this actually work?
Okay, so it is an API.
Okay.
It's a library. The API, there's several APIs. There's one for the parser, one for tables, one for accelerators. So there's different sub-APIs. A lot of it, particularly the parser and the table, the API is what we call declarative representation. When we define a parser, for instance, we've made, over the past 10 years, or actually forever, since the beginning of time, the way people would write a parser is they would do what I call if then else. So they would start with the first protocol, they would do a switch, they would go to the second, and they would kind of run through them. Usually you'll put this in a loop. And I actually explained this in my last blog. The problem with that is when you get a lot of protocols, it becomes really difficult and unwieldy, and it basically you arrive at spaghetti code, because parsing is not a very uniform thing. It's kind of messy. It's really difficult. So running this in imperative code, it works, and we've made a lot of progress. But honestly, anytime you have a significant base that does a lot of parsing, it's really easy to have bugs. So the alternative is really to go back. What actually is a parser? A parser is a parse graph. You can always write it up as a graph. We've seen these since the beginning of time. You have a root Ethernet node, and then that can switch to IPv4, IPv6. And then under that's UDP and TCP. And you can basically build a tree from Ethernet. And then thanks to encapsulations, you actually have backlinks in the tree, so you wind up with a really potentially complex parse graph. But it is a parse graph. It's just a graph from computer science. And the other way to look at it is it's also a finite state machine. So when I'm parsing, I start at one protocol, say Ethernet. I figure out how to transition to the next protocol, make a jump, and I process the next one, which might be IPv4. And then I transition to the next and the next and next until finally I hit a leaf. So the representation is best as a graph. And the mechanics are kind of best represented as a finite state machine running on that graph. And that's exactly how we would code up a parser in XDP2. So what we've done is create a set of macros that create the data structures that map into that parse graph. So there's a parser data structure, which defines a parser. And basically, that just gives a root node. And then you have these things called parse nodes. They describe your parse nodes. So the IPv4 parse node, the IPv6, TCP. You may have parse nodes for options. So whatever little protocol you have, that becomes a parse node. And then we have a way to link these called protocol tables that describe how to go from one parse node to another. And that fundamentally describes the structure of the parse graph and the program. And then what we do is we annotate the parse nodes just a little bit. So in order to actually parse, we have to know two things about any protocol. We have to know the length of the protocol header, and we have to know the type of the next header for a non-leaf protocol. So I would consider those annotations of the parse node. So what happens is when the user writes their program, it's a set of macros to describe that map to different data structures. They start with a parse node, then they just are root in a part on that. They start with a parser structure that points to a root, and then they describe all their parse nodes, and then they describe the relationships between the parse nodes and protocol tables. And then each parse node is annotated with kind of the invariance of how to parse. So that doesn't have to be something the user has to deal with. Usually they can get that information from what we call a protocol definition. So the user writes their program as a sequence or a set of macros. And there's no imperative code. These literally compile in the data structures. And in the first pass, without any optimizations, we just compile that into data structures. We have a little engine that reads the data structures and kind of follows them and does the parsing. So it's a table-driven parsing. That's not great for performance, but that's functionality.
Right.
Now for performance, we do something really interesting. Going back to is there a compiler? There actually is a compiler. It's called the XDP2 compiler. And what it does is it takes something like that parser program that compiles into a series of data structures. It actually does what I call compiles the data structures. So these data structures are static constant data structures. They're invariant, which means the program, if it understands the data structures, it can actually turn that into linearized code. So this parsing where we're going from one parse to a node to another, I can actually compile that into the typical if-then-else imperative code that CPUs like. So you do wind up with the same spaghetti code that we had in the beginning. But the difference is this spaghetti code was generated as opposed to created by humans. So correctness and all the bookkeeping is handled automatically.
Yeah.
And since it started with a clean abstraction, we can actually put a lot more work into optimizing that back-end code. So we can do loop unrolling. We can even look at code paths that are unique and like no branches, and we can scrunch those together into one big function. So we have a lot of opportunities to do fine-grained optimizations. So with this, and by the way, this isn't even talking about hardware. We can compile this from C code into C code that is then compiled into the final executable, but that intermediate kind of C code is that optimized, unrolled version. And some of our tests that I need to revisit before I publish them again, some of our tests showed that this way of doing what we call the XDP2 compiler to produce an optimized C code, that actually produced faster code than what we consider optimized handwritten parsing.
Interesting.
Compilers are powerful. What can I say? I mean, compilers can optimize better than humans can. This is why, people who think they can write better assembly than compilers or outwit a compilers this day and age, it's really not right. And going back to why this is possible today, a lot of it has to do with the compiler advancements.
The FFmpeg guys would beg to differ.
What are they doing?
Writing lots and lots of handwritten assembly code because they find terrible output from compilers.
Well, honestly, if I could get paid to write assembly for a living, I would. But we have to be realistic.
Yeah. So the fact that you compile back down to C code, this kind of optimized C code, that probably gives you then the avenue to be able to compile that into eBPF if applicable, or into maybe even FPGA code that's going to go out on some piece of hardware, right? Is that how that fits together?
Well, yeah, we actually have an eBPF compiler. So that same program that I just described, that same parser program that we compiled into optimized C, we can also compile that into eBPF code. It's kind of the same thing, but when we're dealing with eBPF code, the thing we have to watch out for is the verifier. So we have some intelligence that tries to make sure the verifier is happy. But you kind of get the same thing. We need to compile into restricted C code. C code. It looks a lot like that optimized C code, but we do need to insert some tail calls and put in a couple of other tricks to make the verifier happy. Now, that being said, so in this first path, this is pretty much the parser we're talking about, which actually has a lot of value in itself. In time, we'll add support for more of the helpers, especially table lookups. And again, that will have a backend, a compiler will be involved there, because when we compile a table, it's going to start in that same sort of declarative representation. And now when we go into C code, we obviously want to choose a library. DPDK has some really good libraries for tables. But if we're going into eBPF, we want to choose one of the eBPF map tables that's appropriate. So again, the backend compiler we're hoping can take care of that to abstract out that from the front-end user. So user just writes their program, compiles it 2 different ways, maybe 3 or 4. It's all the same functionality, but they differ by the target.
Yeah.
There are a lot of obvious challenges there. So all the targets may have different capabilities, different resource capabilities. So we have to take that into account. A hardware target may not even have a function that the user wants, like the ability to do hardware encryption.
Right. So that's a question.
You can't magically produce things, right?
That's a question I wanted to ask. Does XDP2? It sounds like we're still sort of early days, but have you thought about like making it automatically split a program? Because you've got certain things that you can do in hardware and certain things that have to do in software. And so if a user could just make one code base and say, this is what I want it to do, and then the compiler says, oh, these parts of it I can do off in this accelerator attached to the NIC, and then the rest of it I have to do in C code and user space. Is that a concept that's in there yet, that idea of like automatically parting between those two types of things?
It's in the design, definitely. My intention is that, and this is another one of those challenges. It's a challenging project.
Sure.
I want to hide as much of that unpleasantness from the user as possible.
Right.
And this is where we've already got pushback, particularly from the P4 community. Apparently, even in P4, between different P4 targets, it's hard to make the back-end hardware transparent to the program. So there's not even P4, there's not even programmability amongst P4 targets. Mm-hmm. So that's challenging. But as much as possible, I really want to hide this from the user. Mm-hmm. So like I said, the user says, I want to encrypt the block of data. If I'm running that in plain user space, I'm probably calling a nice library, maybe using AES instructions. Mm-hmm. If I'm in some hardware context where I have a hardware accelerator living on the side, I want to call that accelerator. And that entails a lot of different things, because that may in fact change the calling program structure and do things like that. But that's why it's important that we have to maintain the user's intent as long as possible. And this is kind of where also a good segue into the AI and machine learning world. So imagine
we haven't touched on that at all.
Well, yeah. Because a lot of this, it's funny because the initial intent of XDP2, particularly compilers, even before this whole vibe coding craze started, mm-hmm. It was saying, let the user express what they want to do in a way that's as simple as possible, and let compilers figure out how to do that in the back end. So make it easy for the user. Now, in the case of a compiler, that's the user writing a program. And then that program, it's just what they want to do. It's simple C or whatever. And then the compiler figures out really how to do it. Mm-hmm. So in vibe coding, and I kind of had, this is my epiphany over the past year, vibe coding and AI, it's the same thing. We want the user to express what they want to do, mm-hmm. and then let the whole system figure out the best way to do it in the back end. The only difference is in the vibe coding, we're saying just let them do it in natural language without any structured programming. Compilers, I'm saying, do the same thing, but provide that structured programming. Mm-hmm. That in itself is actually a big differentiator for compilers, because at this level, especially when we're talking about hardware, we really do need that determinism. Mm-hmm. It's a little worrisome that AI could interpret the same program in different ways depending on the time of day or its mood. Compilers can't do that. So right. I think we are going to need compilers to be kind of leading this, especially at this low level, for a while. So compilers are going to be the ones figuring out what goes into hardware, what doesn't. But that being said, yeah, I think there is a future for AI programming here. It's going to start with being that top level, like writing the data path instead of the user, which is good. But eventually, yeah, I think we'll percolate down to AI. I don't know if it will replace our jobs, but I think it's a good goal to see if we can get it to the point where it can.
Yeah. We could riff on that for a while, but goodness, we're already back at the bottom of the hour. Is there anything that we didn't get to that you wanted to make sure and talk about? We covered a lot, I know.
Well, you said you were going to ask a simple question or a dumb question. What was your dumb question?
I asked a couple of them. The one I was actually thinking of, though, is CXL, Compute Express Link. Is XDP2 doing the same thing as CXL?
No. That's not a dumb question at all. It's a very good question. CXL is more of an interconnect technology. XDP2 would be a protocol on top of that. But that does get into a whole nother topic area that might be probably a good topic in a future discussion. How do we deal with these really, really high performance interconnects? So imagine you're building out a network for AI and machine learning, connecting thousands of GPUs. When we do that, especially in what we call scale-up networking, which is very, very tightly coupled processing, we really, really have to have super low latency, super high throughput, low variance links. And this is where the interconnect technology, PCIe, CXL, starts to kind of come into collisions with more what I call a network technology at the high end Ethernet. But there's some intermediate technologies kind of between them, UA link, NV link. So trying to marshal this whole space, trying to keep everything flexible. XDP2 has a part in the sense that we think this is the programming part of that. But it has to be done, a lot of it has to be done in hardware. There's not a lot of latitude for latency. And the interconnects become super critical. So we have to have a kind of a melding of all of this at a very low level: flexibility, programmability, high performance, interconnect, signaling, all of it has to be really tightly coupled. And then we also have to add how we're going to do inline processing in these high performance data paths. So CXL is a whole nother tangent in itself. It does have a part to play in this new world. But like I said, it's a huge topic. And I think you're going to see continue to see announcements and progress on this. And one of the things I would point out, realistically, at least for the time being, we have to accept that AI and machine learning are driving a lot of the investment in infrastructure. So that's just kind of the way it is. And that's why XDPNet is xdpnet.ai, because we want to be in the AI machine learning infrastructure. Some of it is new, honestly. Some of it is new because of the requirements. But a lot of it is still based on fundamentals and basics. And that's good news because we don't have to completely flip the world upside down. Maybe when we get to quantum networking we do, but until then, I think we're still on the path, still trying to get forward progress, and hopefully XDP2 will be one of those stepping stones to get to the new future.
So is your prediction for what comes after AI? Obviously, we're in the middle of the AI bubble as it is, and I've spent a little bit of time thinking about what comes next. Is quantum your prediction for the next big thing after AI, or is there something in between there?
As a area of computing, yes. It's just too appealing. But I think all of these technologies, they take much longer than we expect. There's a quote that I love from Mark Zuckerberg. It's easier. We can underestimate what we can do, and we overestimate what we can do in 2 years, but underestimate what we can do in 10. That is absolutely true.
Yeah, I like that.
I think 2 years from now, you may look at XDP2 and be disappointed with the progress. It's very possible. 10 years from now, I think it's very likely it'll just be, kind of driving this, because all the technology came up with it. We will have melded hardware and software, and we will be looking for things like quantum computing and quantum networking. So it's a marathon. It's my predictions. A couple of them for eBPF. For instance, eBPF is going to become a mainstay of the kernel. We're going to start to replace parts of the kernel with eBPF. I talked about the melding of hardware and software. I think we're going to solve the offloads problem. That's probably shorter than 10 years. But yeah, I think, and the thing I like about this, especially this 10-year anniversary of all these things, it's really a nice time to look back and see how we were able to introduce several groundbreaking technologies, how they materialize and why they took 10 years, and why they seem to take so long, but also why they were so disruptive and so innovative. And that kind of gives us a blueprint for how to move forward over the next 10 years. It's always an escalator. We're always going to be moving up. I don't see an end in sight to any of these technologies.
Indeed.
But I do think, at some point we do want to start to solve some fundamental problems. So yeah, I'm still an optimist about the future.
Yep. Very good. All right, I've got to ask you 2 questions before I let you go. I do get strongly worded emails when I forget it. And that is, what's your favorite scripting language and text editor?
Python. I've come to accept the fact that indentation matters, even though it still annoys me. Text editor, I guess Vim at this point. I'm not very creative with text editors, so I've been using the same thing for 20 years. It seems to work. So.
It seems okay, yeah. Can we, so to follow on to that, can you write your accelerated code out of Python? Can we talk XDP2 from Python?
I would love to do that. If anyone wants to work on that, please send mail to the list, or you can DM me directly. Having this in Python would be a game changer in a sense.
Yeah.
I would absolutely love to have this in Python. I don't think anything prevents it at all, especially if we can compile the Python. So yeah, Python is high on my list for support, as is Rust. So I think we want to get to those two sooner than later.
Yeah. Seems like maybe a good grad student project for somebody working on
Absolutely, yeah. So for the grad students out there, PhD students, actually I'm getting quite a few of them with interest, which is good news.
That's cool.
Honestly, I was a little bit worried for a while that this area, like systems and kernel, was becoming less popular in schools. But I'm getting a lot of feedback, which makes me have hope.
Yeah.
That there's still people coming up, because we are going to need a lot of work in this area.
Absolutely.
Believe it or not. I think the writing's on the wall, especially when we're dealing with hardware. There's going to be a lot of stuff. We're going to need a lot of low-level developers to work on this stuff, and it's not the kind of programming that AI is going to replace anytime soon.
Yeah.
So yeah, if you want job security, this might be where you want to look at.
Very good.
Sorry, I had to say that.
No, it's all good. Tom Herbert, thank you so much for being here. It is a delight as always. And I don't know how the almost hour and a half, flew by so fast, but it was a lot of fun.
Sorry about that.
No. It's absolutely fine. Appreciate you being here.
All right.
All right.
Thank you. Thanks for having me. It was a joy, as always. You guys ask good questions. And I hopefully I can come back someday and continue our discussion.
Absolutely. All right. Rob, what do you think?
I completely agree with his Python indentation frustration. I know you've heard me say that one before. Otherwise, about XDP2, I'm definitely curious to see how this improves networking performance in the future. But right now, there is a lot to digest. I'm going to have to check out his blog and the project for myself.
Yeah, absolutely. It's not the level of networking that we work with. Let's be honest. It's the level of networking that I don't know. I don't even know that your ISP pushes enough bytes to need this sort of thing.
No, I don't think we're in that space yet.
Yeah, not yet. But it's still fun. It's still fun to play around with and think about and hear what's going on. But let's be honest, this is the sort of stuff that's going to run at Google and Facebook and those kind of places that are on the exascale. But yeah, good stuff. Is there anything you wanna plug before we let folks go, Rob?
For those looking to see more of me, you can come see me with Jonathan and the Untitled Linux Show, or you can find my website, robertpcampbell.com, and links to connect with me at Blue Sky, LinkedIn, and all those places.
Yes, absolutely. All right, appreciate you being here as well. We have a guest for next week. Let me scroll to the right place on the spreadsheet. We're talking with Paulus Schausen about the Open Home Foundation. That's Home Assistant and ESP Home, Music Assistant, some very, very interesting things there that I'm looking forward to. Not sure who's going to co-host that yet, but we're going to get somebody. And so appreciate, hope everybody comes back for that. If smart home is your thing, that's what we'll be talking about. If you want to find more of me, well, Usually that's Hackaday. That's Google Chat. Don't try too hard to read that. I'm going to have to blur that out in post. But you can find more of me at Hackaday. That's where the security column goes live every Friday morning, and that is also where Floss Weekly is at. And then there's also the Untitled Linux Show, twit.tv/ULS, and we would love to see everybody there as well. We appreciate everybody that watches and listens, those that get us live and on the download, and we'll be back next week on Floss Weekly.